Okay, hi everyone. Welcome to our 44th session of the MedAI Group Exchange. This week, we have Ramon from ASU here with us to lead a discussion on fair AI model development for image classification and prediction. Ramon is a PhD student in ASU's Data Science, Analytics, and Engineering program. His research interests involve studying model debiasing techniques. Previously, he completed his undergrad studies at East Western Reserve University, majoring in biomedical engineering. Thank you so much, Ramon, for joining us today. Before we start, could you tell us how you want to take questions?
In between the presentation, since we're going several papers, I think that's probably easier.
All right, sounds good. So as always, let's try to make this session as interactive as possible. Without further ado, let me hand it over to Ramon.
Okay. Thank you for the introduction. Let's get started with the slideshow. Okay, so as previously mentioned, I'll be doing presenting a review that we worked on for the past year or so on fair AI model development. So we currently submitted the review we submitted it, and we're currently going through the actual review process. And I'll just be presenting a few of our findings or the papers I found most interesting. So why do we care about these fair AI models? So a few years ago, I think everybody's heard about this study that was trying to predict recidivism in inmates, and where they identified that the risk of recidivism was much higher for African Americans and other individuals, independent of their prior offenses. And here's one example where one individual has one petty theft offense. Meanwhile, the other individual has several more, and anybody would have suspect that they would be most likely to commit another one. And they did end up actually committing another subsequent offense. But we are more in the medical field, so we kind of have to look into how can those type of biases that model learn might influence our models. So one paper, the exclusion paper, had demonstrated that there does appear to be some sort of disparity when it comes to image diagnosis models. So in this paper, what they did was compare the true positive rate disparity amongst different demographic groups for classifying or predicting certain common diseases through chest x-rays. And here you can see that for some cases, the white demographics, which is usually the majority, it has a much larger true positive rate compared to the other demographics, meaning that there is a greater benefit to treatment. Meanwhile, for other populations, especially minorities such as Hispanics, you see that their true positive rates is lower compared to the average, meaning that they might not have access to care. A non-imaging related version of this was this additional study where it had shown essentially if you have a model that's trying to predict risk of severe chronic disease. Here you can see that for comparing Black and white patients for the same risk score, they actually had very different levels of active chronic conditions. So let's say for a Black patient with a risk score of 50 might be more comparable to a white patient with a risk score of 70 or so, which will definitely have some impacts on downstream healthcare decisions if you were to apply this algorithm in clinical practice. And as an additional example, here's from that same model, different levels of, let's say, hypertension and what their corresponding risk scores was. So you'd see that Black patients would have a much higher level compared to their white counterparts, but a much lower risk overall. But these models, through several different data cleaning processes and careful studies, you are able to develop a fair model. And in this presentation, I'll just be going over several different techniques to develop these fairer models and see what potential challenges there are in making these fair models. So we will first start with just creating fair data sets. So the idea here is that perhaps the models aren't just seeing enough of a variability in your data, and perhaps it would be better if you had a more demographic a data set that has greater demographic variability, and therefore it wouldn't learn some of those biases. And in this case, we have the fair crowd model, where basically what the attempt is to take this data set that might have different proportions of genders and race and age, and try to develop a smaller data set that is more representative and has fairer outcomes. And in this paper, the way that they define fairness is using the equalized odds, which is basically for given a data set, a model, and a certain demographic label. So that's the A plus and A negative here. So let's say for male versus female, ideally a fair model, the true positive rate differences should be very small. For like, let's say for detecting smiling or yeah, so for detecting smiling, the model should have a very low difference in the true positive and the false positive rates. And the way that they go about doing this model, well, it's more of a process that involves several different models. Is four processes where they have this batch selection where they try to identify what demographics are not being predicted correctly. And here they try to see, oh, is it more predominantly male or female? And then based on that predominance, they then try to label each image in the data on whether it's belonging to that majority group or not. And using that group membership and they will then assign if image should go in this new training data set, yes or no. So now we'll just go through each of the individual steps. So first is identifying the batches that are correctly being predicted. So in this study, what they first did is that they didn't have demographic labels for the images, but they could try to group images randomly, whether they were correctly classified for the task or incorrectly classified. So here as an example, you have a batch that according to the paper was not correctly classified, and the one below was correctly classified. And then using those batches, they use crowdsourcing. So through Amazon Turk, they had manual annotators label each data set as being each batch as being either predominantly male or predominantly female. And I believe in this case in particular, it's a slightly predominantly female data set, batch. So now, once that they've established whether all the batches are either predominantly male or female, they take every image on the data set and they try to essentially, using similarity, try to infer what the demographic of that particular image or individual is. So in this case, in a predominantly female batch, the image of a woman might be more similar to all the other ones by doing simple cosine similarity of the representations of a model. So actually, to backtrack a little bit, to measure the similarity, they take each image and they put it through a CNN called FaceNet, and they get the embedding vectors from that CNN. And then they just do cosine similarity to compare, let's say, the leftmost image with this new image. And ideally, by seeing which ones you're most similar to, you'll either indicate that this is most likely a female, an image of a female, and then just go on from there using those labels. Then is where it kind of gets more interesting. So since they're using the Celebe data set, the way they were able to track like how the data set was being shuffled around every single iteration. So at the very beginning, they had a skewed sampling of the data. And from that skewed sampling of the data, every single iteration of predictions of demographics, um, you see that the model is able to then select, increase the number of male or female older individuals, and to create that more balanced data set, as one would say. And now so any questions on the method so far?
I have a question about all
Mm.
the using the pre-trained CNN.
Mhm.
So if the pre-trained CNN is already biased, would that impact like potentially yeah, the reassignment or like adding or removing, or
Well,
did they
yes,
discuss anything about that, about this like pre-trained model being biased?
yes, but in a way, you almost kind of benefit from it being biased, because let's say because of the one thing you want to do is identify people belonging to a certain group. So if there's more of a group for, so this is a face detection model. So if there's more bias towards, let's say, females or males, it will group males more closer together, let's say. So
I
I think
see. Right.
in a way, you kind of benefit from the bias in this case. Yeah.
I see.
But let's say for other attributes, let's say if you were using other attributes, like let's say age prediction, like if they're older or younger, then that's where it gets a little bit more difficult, because the predictions couldn't be, let's say, completely off then.
Yeah, got it.
Yeah.
Thanks.
So it's not necessarily an optimal choice. Okay. But the one thing that we do see is that, so if you compare training, let's say, any common models using that random data set and this new sample data set, should we say, you see that overall the fairness performance metrics do improve quite a lot. So in a way, they did achieve their goal. And there's not much else about this besides the improvements on overall performance. So we'll move on to the next paper. And this one over here is seeing how gender imbalances could affect the performance of medical imaging datasets. So in this study, what they did is that they took the NHS X-ray dataset and CheckSpert, and they tried out to see if, let's say, you had different percentages of male, female in your training data, how would they generalize to a separate test set and what they find is the following. So if you train a model on a predominantly male data set, testing on just male patients, it will end up performing well. But if you train it on predominantly female patients and testing on males, it's going to perform slightly worse. And there's going to be a slight significant difference for certain categories. So you can see here from the chest x-ray, from the CheckSpert labels, it kind of switches between which categories there's significant differences and which ones there's not a significant difference. But still quite shocking to see. But in the real world, you would say that you're not going to encounter a data set that's just predominantly male, predominantly female. You might have like subtle differences. So what the authors did is that they compared, so let's see what happens if we have a 25, 50, or a 75% split. And what's very interesting here is that if you have a model that has the 50-50 split, it performs just as well on, let's say, on the male only test set, as well as the model that was only trained on male patients. And the same would apply for the female data set for several different classes. So almost as if, and by showing that having an equal proportion of, let's say, positive labels for each of the models. Okay, sorry. Okay. I was getting Slack notifications. Meeting. Okay, yeah. So by having equal proportion of positive labels, you can end up having a much more robust model in your evaluations on if you're basing off of gender. And this could perhaps extend towards, let's say, demographics, which we've seen in other studies. And kind of the takes away here is that we could most likely, by increasing the diversity of our data sets, we might be able to train much better models than just having, let's say, a large skewed data set. And we can exploit different techniques to try to identify what the informative data set would be. But in some cases, we can't really have a balanced data set. So we have to figure out ways to learn better representations or have models learn to be agnostic to these differences. And this section is just going to cover those, how to make your models unlearn any biasing features that might be occurring in your data. So one example of this is in this other face attribute detection model, where if you look at the embeddings, there are certain features that are very clustered separately on a traditional baseline model. So here, based on male versus female, there's very consistent clusterings occurring, as well by this other group label is ethnicity. And in this paper, what they're going to try is, by trying to preserve the privacy of individuals, of removing, let's say, gender and ethnicity, if you can generate both a better model and a fairer model. So in this case, the authors almost stumble upon a fairer model by trying to improve performance. So here, the architecture is a little bit involved. So unlike other studies where they try to train a new model that's fair, here they try to change the representations of the model so that they're more fair and have removed any of this identifying information. So they take your standard pre-trained model and they train several linear layers that are meant to create a new projection where you are no longer able to distinguish between gender or ethnicity. And the way that they do this is through the use of combining two loss functions here. One is for the demographic identification, and then triplet loss for classification. So here, the triplet loss makes sure that each individual patient or identity is separate. So that way the model is still useful for identifying unique individual features, but we are penalizing it by making sure that the model cannot classify any demographic information in the model. So let's say there should not, your anchor or your positive or your negative samples, you should not be able to tell if it's a male or female or from a certain group. So to evaluate this model, they use the dive-based dataset that has 6 different classes. Sorry for the slight figure issue. So each of these 6 identities are split amongst male, female, and then whether they're darker skin, lighter skin. And let's go. So going from there, they so since you're kind of modifying the weights that the model learns, not the weights, the embeddings that the model learns later on, you can kind of test before and after how well the model is for one recognition, but also how useful those features are for identifying, let's say, gender and the ethnicity. And what the authors found is that they do get a large reduction in both gender and ethnicity recognition, but their loss in recognition performance is only a 5% loss. So this being accuracy, this is a pretty small, I would consider it to be a pretty small loss compared to how much the ability to identify gender or ethnicity is. Any questions about, oh, okay. And just to show that the information is actually being removed, here you can compare the embeddings of the beginning of the network before they do any of the sensitive information removal, and then afterwards, where you can see that now all the demographic information is just everywhere. And the other thing is that they compared it to other debiasing techniques. So learning not to learn, being the adversarial debiasing network, where it's basically a model that is penalized for learning a certain demographic attribute. And one thing you can see is that the performance is slightly better compared to the other models, especially for the domain task. So the main task being either predicting attractiveness or smiling. Any questions on this part?
So do you know, like, what is the training data distribution for this one? Like, is it the same for all the subgroups or no?
Oh, yes, sorry. So in this case, the number of identities per each of the classes is the same.
Okay.
So they try to keep that as matched as possible.
But like, if you can go back to the network architecture ones, but do you think that, specifically the loss, can you go back to the loss ones? Yeah. So do you think that if we don't have the equal subgroup for all these sensitive attributes, do you think that that may affect this particular training loss? Because since we don't are not using any kind of like balancing or any weighting factor in the advisor regularizer.
I'm not sure I understand. So
okay,
I'm not
so
sure
imagine like the 6 subgroup that we are showing, right? So imagine one subgroup has like very few cases. Do you think that that could be still applicable, this particular loss formulation? Because I personally feel like probably if you don't have equal representation in all the subgroups, that may also affect the separation, right?
Yes, I see. Yes. So I agree with that. And some of the other papers we'll discuss later on, they actually get into discussing how to go around that issue.
Okay. So did they highlight that is a
Mhm.
limitation in this paper or no?
I do not recall seeing that as one of the
Okay.
limitations.
Okay.
Yes, but let's see here. I think so. Not this paper, but the next one, the final one, will cover how to go about those limitations. So in this case, for this one here, instead of trying to penalize using, let's say, the triplet loss, you can simply add another branch to your model where you are penalizing for learning some biasing feature. And in this case, the loss that they are adding is the correlation. So traditionally, you would expect here the loss to be based off of cross entropy. Basically, oh, if you're learning this demographic or this domain feature, we're going to penalize it more. But the authors and several other papers argue that just doing the correlation might just result, not correlation, cross entropy might just see a shift in the probability values that the model outputs, and not necessarily remove the correlation of the features. So in a way, there's still some information regarding the domain being present. And studies that have compared both of these losses have kind of shown that the correlation loss appears to work better, at least for removing domain information. Okay, so the way that they try and evaluated this model is on this HIV data set where they're trying to establish brain age from looking at images. And one challenge here is that on the images for the individuals with HIV, their images might appear older than, let's say, a healthy individual. So therefore, there's a biasing component there. And one approach that they do here is that since the HIV prediction, one, they have a slight imbalance in their data. Plus also since the HIV age estimation can't really be trusted in a way, their debiasing for age is only focused on the controlled or healthy individuals. And just to see like the effects of the correlation compared to using the correlation loss compared to other methods is here. You can see just the vanilla CNN and how well its features correlate with the domain feature, or in this case being age, and a multitask model. So a multitask model being just a two-branch model where it's actually trying to learn both. So it makes sense that this one would have the highest performance. And then you have two other models that are using the cross entropy based losses. And you can see that they have a slightly higher correlation going on. They still see a slight reduction, but not as significant as the proposed model's correlation loss. And here we have how their overall model ends up performing. And one caveat I would say about these representation learning models is that they will always perform slightly lower than, let's say, the vanilla or baseline models. So in this case, you see that it's almost very close to the vanilla model and the multitask one, but they are performing much better than the other debiasing techniques. And we can see that they do obtain better performance in once you see like the more fine-grained performance metrics. So the F1 score, we see some much larger improvement compared to all the other methods. And the balance accuracy, we also see the same. Then moving on there is they also tried to do an experiment where they were predicting gender on images. And one thing that they did is that they tried to see in like skin color as a biasing feature. And basically what they found was that their model does have an improvement in the average accuracy compared to the other performing models, regardless of backbone. And well, this is just the overall results that they outdo the other ones. But what I think is more interesting is comparing the embeddings of the models. So the one thing is here, you can still see in their BRNet that there might be like some grouping, but the overlap is greater than, let's say, the other groups where there seem to be distinct clusters occurring. So in a way, you could say that the model has at least learned to does not learn to separate based on the skin color feature anymore, or its ability is reduced. Then moving on from there, and then we're at the final paper, which is where we attempt to unlearn dataset biases. Again, trying to do confounding removal, which is very similar to the previous one. But this time they are doing a 3-step process, where before it was like a single step. here it is 3 steps within the training loop that are occurring. So first, you wouldn't have to train your feature extraction model or your backbone. And in this case, you're just training for your classification loss. So this could be any loss that you would need for your downstream task. And in this case, they're averaging over each different sample that or domain that they would have. In this case, the different domains are different types of scanners for MRIs. Then you want to so in order to, in this case, unlearn the features, you first need to have this adjacent classifier that's actually able to predict the domain that the data is coming from. So first you have to train a model that is able to tell that, oh, this is scanner A versus scanner B. And then finally is where you are penalizing the model for learning those features. And now you are basically unfreezing the backbone of the model and freezing the domain classifier. And you're just having the backbone be penalized for learning any features related to that domain. And if you keep altering these steps over several epochs, the model will eventually learn to forget these features. And so here is a data set that they obtained. It was an MRI data set from the Biobank, Oasis dataset, and Whitehall. And one thing which Iman had brought up earlier is what happens when your data set is skewed. How will your model unlearn those features? And the one thing that the authors did is, since there's such a skew in the distributions, what if we only tell the model to unlearn based on overlapping distribution? So in this case here, you can see that Biobank and Oasis have very different distributions in age. And they test out if they only unlearn similarities. So in steps 2 and 3, they're only using patients in this black bar over here. And then they try to increase the overlap and see how that influences the model. Okay, so here is the average age estimation ability for each of the model and for their model trained on different data set splits. They're comparing just a normal training algorithm where they just try to balance the model. Try to balance the data set versus using the unlearning paradigm. And the task was estimating the overall, the age of the patient. And we can see the average error is lowest for using all 3 data sets. One second. Yes. So using all 3 data sets, the model performs best, regardless of you're doing normal training or unlearning. But the unlearning seems to do slightly better on most of them. And then also it loses the ability to detect the scanner where it's coming from. And just to compare how different each of the scanners were, here are the TSNE embeddings of the features before and after the unlearning process. Okay, and here's what I would say is the more interesting part is, so here they tried to, this is the overlap component I was referring to, which is only unlearn using a 5-year overlap, a 10-year overlap, or this 15-year overlap. And what we've what I would have expected at least is that on the smaller overlap, maybe the model would have learned better, and therefore they would have seen the most improvement there. But actually using the widest overlapping criteria is where you see one best overall performance on the mean absolute error. And then on the scanner detection, the lowest performance is actually on the 15-year overlap. And also, I might have forgotten to mention this, the 50 in the brackets is just random chance. So if you had a random model predicting what the accuracy would be for those. So then moving on from there, I think earlier we had mentioned that you just using your general loss function. The reason why was because the authors tried to introduce this method as being both for classification and segmentation. So for segmentation, there's only a slight twist to it where you're using both the final output and also the features from the bottleneck layer of your segmentation model. So using those same features, you can train your domain classifier, you penalize your model backbone for learning those domain features. And once you go through that process, so I think, oh, okay, sorry, I accidentally hit it twice. Once we go through that, we see that the one that has the best overall average performance is again the model on learning, which sees better improvements for Biobank and Oasis. While if you train on each data set individually, that's the second highest performance. So if you only train on Biobank, you'll have really high performance on Biobank. Only on Oasis, then you'll have really high performance on Oasis. And then meanwhile, the on learning on both does very well across either. And I guess here, the kind of the takeaways for these models would be that if you just using simple loss functions, either the adversarial regularizer that we saw, or adding a penalty term on the correlation, we can see some improvement on overall performance. And we kind of also have to be very careful on the debiasing step on how we are balancing or which samples we're using to penalize the model. And that is it, what I have. Any questions or?
Great, thanks Ramon for the presentation. It's very interesting to know the studies are working on different areas, but with a similar goal that of debiasing and also like creating unbiased data sets. Any questions here from the audience? So Ramon, I have a question. Since I believe you have seen a lot of paper about debiasing, I feel that some of the papers you have presented are pretty domain specific. Like the techniques they use are, they only focus on like a specific domain such as facial recognition or like medical imaging, MRI. Have you seen any paper that's more that developed a debugging technique that's more general? Yeah.
Yes, so I can actually refer, so some of these papers I only included in, let's say, one application. So let's say this one, they also had, let's say, the income data sets and like on tabular data. So this paper in particular, I would say was more general. So I think mostly a lot of papers are split either between imaging or let's say text data. And within those, there's pretty general. There's some with metric learning that I would say try to be rather general. So they do both natural image and medical imaging domain. But both of these approaches, so actually, let's say this removal of this biasing feature is kind of an extension of some work that existed in the NLP domain. So there's technically not, so if you're just comparing, like say, embedding vectors, there's nothing that stops you from either applying it on images or on text.
Right.
Yeah.
That makes sense.
Yeah.
So Raman, what other like limitation that you found in this particular area?
So one of them is that you kind of have to be aware of what your domain or class is in a way. So you kind of have to be aware where the problem is. So let's say you almost have to train a model, then see where the bias is, and then almost like go back to train it. And sometimes you might not have access to that data. So like, let's say age and demographic information. I wouldn't say all imaging data sets that, let's say, are publicly available, they would not have that information. And sometimes the bias features are pretty hard to figure out, because it could be that, oh, the bias is due to scanner or the type of patient, like how sick they are already. So it's very difficult to find out where the bias is coming from to begin with. I think except for like the HIV case where they expect there to be a very significant difference in age. In other tasks, especially like, let's say with race, it's very hard to pinpoint where the bias is coming from.
Okay. Okay. And since you particularly present like two parallel branch of reducing the bias, one is through dataset and one is through the representation learning. So if you get a task in hand, which kind of applications or which kind of method you would be fast exploring based on these two branches, like creation of a fair dataset versus creation of a fair representation learning?
So in that case, I think the initial model sometimes that we train, let's say, I would go first for like a balanced data set in a way, but that's usually not a luxury that we have. Let's say we might not have enough samples. So I would go towards more the representation learning route as a preferred option for trying to improve fairness in general.
Okay. Okay.
Yeah.
Makes sense.
Okay.
Okay.
Any other questions? If not, let's give Ramon a round of virtual applause. Thank you for the great presentation. And thank you everyone for joining us today. We will upload the recording of this talk to our YouTube channel later. See you at the same time next week.
Thank you. Bye.
Thank you.
Thank you.